Something is happening on Jupiter, and NASA is not giving you the full story. On Christmas Day, 2023, scientists aimed the most powerful space telescope ever built directly at the largest planet in our solar system. And what they found shattered 4 decades of assumptions in a single observation session. A light so bright, it had no explanation. A temperature structure that defied every existing model. A storm that has been dying for 150 years but refuses to disappear. What you have been told about Jupiter is incomplete. And what they are finding now changes everything we thought we knew about our solar system. There is a planet in our solar system that has been staring at us for 4 centuries. Galileo pointed his primitive telescope toward Jupiter in 1610 and saw 4 moons dancing around it, and humanity has never stopped looking since. We have sent 9 spacecraft past it. We have photographed it from Earth with instruments powerful enough to read a license plate from orbit. We have studied its storms, its magnetic field, its moons, its rings. And yet, right now, in 2025 and 2026, NASA's most advanced instruments are returning images and data that are forcing planetary scientists to sit back in their chairs and say out loud, in peer-reviewed journals, "We do not understand this planet. That is not a metaphor. That is not scientific modesty." That is the actual conclusion being drawn by researchers at Northumbria University, UC Berkeley, the University of the Basque Country, and the European Space Agency. Jupiter, the planet we have been studying longer than any other in our solar system, is revealing secrets that nobody predicted, nobody modeled, and nobody can fully explain. And the deeper the James Webb Space Telescope looks, the stranger it gets. Let us start with what should have been a routine observation. On December 25th, 2023, a team of astronomers aimed the James Webb Space Telescope at Jupiter's North Pole. They had a very specific target, the intense auroras that surround the planet's magnetic North Pole. While these Jovian northern lights had been imaged before using the Hubble Space Telescope, Webb provided an unprecedented view, capturing details of this phenomenon like never before. They were not expecting surprises. They were expecting to confirm what Hubble had already shown them. Colorful, energetic, magnificent auroras, bright and beautiful, ticking all the known scientific boxes. What they got instead was something that, in the words of the scientists themselves, left them scratching their heads. The dancing lights observed on Jupiter are hundreds of times brighter than those seen on Earth. But here is where it stopped being routine. The team uncovered unexplained observations in their data. Bizarrely, the brightest light observed by Webb had no real counterpart in Hubble's simultaneous ultraviolet pictures. Read that again. The brightest signal that the most powerful infrared telescope ever built, detected on Jupiter's North Pole, a signal so intense it dominated the entire dataset, simply did not exist in the images taken by Hubble at the exact same moment. 2 telescopes, same planet, same time. Completely different realities. This is not a calibration error. This is not instrument noise. Both telescopes were cross-checked, verified, and double-analyzed. The signal is real. The absence in Hubble's data is real. And what that tells scientists is that something is happening in Jupiter's upper atmosphere at a wavelength and energy range that no one was looking for, in a layer of the planet that no prior model predicted would behave this way. The question is not whether this is significant. The question is how significant it truly is. And the more they study it, the bigger the answer becomes. An international team of scientists revealed a never-before-seen temperature structure and dramatic density changes within the top of Jupiter's atmosphere, particularly in the northern auroral regions. Think about what that means for a moment. We are not talking about fluctuations within a known range. We are talking about a temperature structure that simply did not exist in any prior scientific model of Jupiter's atmosphere. The planet has a layer of behavior up in its high atmosphere that we never knew about, that we never predicted, and that we are only now beginning to map, because we finally have a telescope powerful enough to see it. The team's data found that the emission from the trihydrogen ion, known as H3+, is far more variable than previously believed. These observations will help develop scientists' understanding of how Jupiter's upper atmosphere is heated and cooled. This matters enormously. H3+ is not just a molecule. It is a thermometer. It is one of the primary ways scientists measure the energy budget of a gas giant's upper atmosphere. When it behaves unexpectedly, when it fluctuates wildly beyond predicted ranges, it means that the entire energy balance of Jupiter's upper atmosphere is different from what every textbook, every model, and every simulation has told us for the last 40 years. The planet is doing something with heat and energy that we did not account for, and we do not yet know why. But here's where it gets worse, or more accurately, where it gets bigger. Because the auroras were not the only surprise waiting in Jupiter's atmosphere. Go back a little further to October 2023, when the James Webb Space Telescope turned its infrared eye to a different region of the planet entirely. Scientists were studying the equatorial zone, mapping the cloud layers, tracking the famous banded structure of Jupiter's atmosphere. And in that data, hidden in the infrared signatures above the main cloud deck, they found something that should not have been there at all. NASA's James Webb Space Telescope discovered a new, never-before-seen feature in Jupiter's atmosphere, a high-speed jet stream spanning more than 3,000 miles wide, sitting over Jupiter's equator above the main cloud decks, a jet stream on Jupiter that is 3,000 miles wide and positioned high above the visible cloud layers that every telescope before Webb had ever managed to study. And this was not a gentle breeze. The newly discovered jet stream travels at about 320 miles per hour, twice the sustained winds of a Category 5 hurricane here on Earth. It is located around 25 miles above the clouds in Jupiter's stratosphere. To put that into perspective, a Category 5 hurricane, the most destructive storm classification on Earth, has sustained winds of around 157 miles per hour. The jet stream that James Webb just found on Jupiter is blowing at more than double that speed, continuously, across a band of atmosphere that stretches 3,000 miles from edge to edge. This is not a storm. This is a permanent high-altitude river of wind that has been howling above Jupiter's equator for an unknown length of time, and we had absolutely no idea it existed until a few years ago. "This is something that totally surprised us," said Ricardo Hueso of the University of the Basque Country. "What we have always seen as blurred hazes in Jupiter's atmosphere now appear as crisp features that we can track along with the planet's fast rotation." And this is the part that needs to sink in. Scientists were not looking for this jet stream. They were not running an experiment designed to detect it. It simply appeared in the Webb data, fully formed, enormous, fast, and completely invisible to every instrument that came before. Which raises an uncomfortable but unavoidable question. What else is hiding up there? What other features exist in Jupiter's atmosphere that our previous telescopes simply lacked the power to see? The answer, based on everything Webb is now returning, is a great deal more than anyone expected. Now, the jet stream and the auroral mysteries are extraordinary on their own, but they exist within a larger context of Jupiter that is itself becoming increasingly strange the more carefully we look. Consider the Great Red Spot, arguably the most famous storm in the solar system. A swirling vortex of wind and cloud so large that it once contained 3 entire Earths within its diameter. For centuries, it has been the defining visual feature of Jupiter, the thing every schoolchild recognizes, the thing that makes this planet feel ancient and permanent and unchanging. It is changing, and nobody knows how to stop it. Jupiter's Great Red Spot is shrinking. The biggest windstorm in the solar system has been slowly declining for decades. Research published in 2024 found that there are fewer storms feeding this giant anticyclone, causing it to shrink. A storm system that has persisted for at least 350 years, and possibly much longer, with some researchers arguing it has been raging for over 400 years, is now diminishing. The winds are still ferocious. The winds of the Great Red Spot consistently blow more than 200 miles per hour, but they can reach speeds over 400 kph further out. But the storm itself is contracting. The massive engine of chaos that once dwarfed entire planets is getting smaller year by year, decade by decade. Though once big enough to swallow 3 Earths with room to spare, Jupiter's Great Red Spot has been shrinking for a century and a half. Nobody is sure how long the storm will continue to contract or whether it will disappear altogether. And here is what makes this particularly unsettling from a scientific standpoint. The disappearance of the Great Red Spot is not just a cosmetic change to Jupiter's appearance. This storm is part of Jupiter's atmospheric circulation system. It interacts with cloud bands, with other smaller storms, with wind currents across the entire planet. If it disappears, if this centuries-old engine of atmospheric energy simply stops, scientists have no reliable model for what happens to Jupiter's weather systems in its absence. The planet's atmosphere could reorganize in ways that are entirely unpredictable. The Great Red Spot's color has been deepening too, becoming intensely orange since 2014. Researchers aren't sure why that's happening, but it's possible that the chemicals which color the storm are being carried higher into the atmosphere as the spot stretches up. At higher altitudes, the chemicals would be subjected to more UV radiation and would take on a deeper color. In some ways, the mystery of the Great Red Spot only deepens the more closely it is observed. It is shrinking in width, but growing taller. It is becoming more circular and more intensely colored. It is behaving, in a word, strangely, in a way that no computer model predicted and no prior observation suggested. And this is where everything changes, because the mysteries of Jupiter's atmosphere, the invisible jet stream, the unexplained auroral light, the dying storm, they are not isolated puzzles. They are all connected to a much larger question that scientists are only now beginning to seriously confront. What is actually happening inside Jupiter? Jupiter's swirling storms have concealed its true makeup for centuries, but a new model is finally peeling back the clouds. For most of modern science, Jupiter was treated as a relatively simple system, a massive ball of hydrogen and helium surrounded by colorful cloud layers, orbited by interesting moons. But the more precisely we measure it, the more complex it becomes. The jet streams run deeper than expected. The magnetic field is stranger than expected. The interior layers interact with the atmosphere in ways that were not predicted by any existing model. Jupiter is not the simple gas giant that textbooks described. It is a dynamic, layered, extraordinarily complex system whose internal mechanisms are still producing surprises at the surface. And if the planet itself is more mysterious than we knew, then its moons, which have always been scientifically fascinating, become even more important. Because one of those moons has been at the center of one of the most profound questions in all of science. Is there life beyond Earth? Europa, slightly smaller than our own moon, covered in a shell of cracked, shifting ice. And beneath that ice, according to decades of research, a global ocean of liquid water. An ocean that could be, by some estimates, twice the volume of all the oceans on Earth combined. For 30 years, since the Galileo spacecraft first returned evidence of that hidden ocean in the 1990s, Europa has been the single most compelling candidate in our solar system for extraterrestrial life. James Webb Space Telescope has captured the auroral footprints of Io and Europa, providing spectral measurements for the first time and revealing extreme changes in the physical properties within Io's auroral footprint that are likely linked to electrons crashing into the top of Jupiter's atmosphere. The moons are not passive bystanders to Jupiter's energy. They are actively connected to it. Their gravitational interactions, their magnetic signatures, their material outputs, all of it feeds into Jupiter's magnetosphere and back into the planet's atmosphere. The system is entangled in ways that science is only beginning to map. But here is where the story takes an unexpected turn. Because while Europa has been celebrated for decades as the most likely home for alien life in the solar system, the latest research in early 2026 has introduced a sobering possibility. A new study, published in Nature Communications in January 2026, suggests that Europa's seafloor likely lacks the geologic activity needed to sustain life. The researchers, from Washington University in St. Louis, concluded that the seafloor might be quiet and lifeless. The findings are based on Europa's size, its rocky core, and Jupiter's gravitational influence. This is not a minor. Footnote. For 30 years, the scientific community's best hope for finding life in our solar system was a warm, chemically rich, geologically active ocean on Europa, one where hydrothermal vents might pump heat and nutrients into the water, just as deep-sea vents on Earth support thriving ecosystems in complete darkness. That was the model. That was the hope. And now, a peer-reviewed study in one of the world's most respected scientific journals is suggesting that Europa's seafloor may simply be sitting still, cold, dark, geologically inert. And if there are no hydrothermal vents, if there is no geological activity pumping energy into the water column, then the base of the food chain that life requires simply does not exist. But, and this matters enormously, it is not the final word on Europa. Other studies have hinted at potential habitability, including in lakes within the icy shell above the ocean. NASA's Europa Clipper, which will arrive at the moon in 2030, should be able to give more definitive answers. So the question is not closed. It is simply more complicated than it was. And complication, in science, is usually a sign that reality is richer and more surprising than the models assumed. Because at almost the exact same time that one study was dimming hopes for Europa's deep ocean, another was rekindling them from a completely different direction. A series of experiments in 2025 support spectral data collected by the James Webb Space Telescope that found evidence that the icy surface of Jupiter's moon, Europa, is constantly changing. Europa's surface ice is crystallizing at different rates in different regions. The surface is not static. It is dynamic, shifting, crystallizing in a process that suggests ongoing interaction between the surface and whatever lies beneath it, which means that even if the deep seafloor is quiet, there may be exchange happening at shallower levels. Material moving between the ice shell and the ocean beneath, potentially carrying the chemical ingredients that life requires. The picture that emerges from all of this is not a simple one. Jupiter and its moons are not a solved system. They are an active, evolving, deeply complicated system that continues to surprise us every single time we look more carefully. The jet stream we never knew existed, the auroral light with no counterpart in ultraviolet, the temperature structures that no model predicted, the dying storm that may be reorganizing the entire planet's atmospheric circulation, the ocean moon that might support life, or might not, and which we will not be able to answer definitively until a spacecraft arrives in 2030. And here is what the scientific community is confronting. Very quietly, in the language of papers and press releases that most people never read, we built our models of Jupiter based on what we could see. And what we could see, it turns out, was only the surface layer of a planet whose true complexity runs far deeper than anyone anticipated. The James Webb Space Telescope has not simply given us better pictures of Jupiter. It has revealed that Jupiter is a fundamentally different planet than the one that lived in every textbook published before 2023. The atmosphere has hidden layers. Those layers contain phenomena, jet streams, temperature gradients, energy imbalances that previous instruments were simply blind to. The auroral system is connected to the moons in ways that are stranger and more dynamic than any prior model captured. And the energy budget of the entire planet, the way heat flows in and out of its atmosphere, is not balanced in the way we thought it was. What most people are not seeing is the implication of this for our understanding of planetary science as a whole. Jupiter is not just a planet we happen to orbit near. It is the largest, most powerful, most complex planet in our solar system. It is a gravitational shield that has been deflecting incoming asteroids and comets away from the inner solar system. For billions of years, many scientists believe that without Jupiter acting as this gravitational guardian, Earth would have been bombarded far more frequently, and complex life may never have had the stability it needed to evolve. Jupiter is, in a very real sense, a co-author of the conditions that made us possible. That should feel significant, because if Jupiter, a planet that sits in our own cosmic backyard, a planet we have been staring at for 400 years, a planet we have sent multiple dedicated spacecraft to study, is still revealing new jet streams, new atmospheric layers, new auroral behaviors, and new mysteries about its moon's potential for life, then the question naturally follows, what else don't we know? What other fundamental features of our solar system are hiding in plain sight, waiting for us to build a good enough instrument to finally see them? The Webb telescope is 3 years into its science mission. It has an expected operational lifetime of at least 20 years. The discoveries that are already emerging, from Jupiter's hidden jet stream to the strange auroral signals that left researchers baffled, are early results. We are, scientifically speaking, at the very beginning of what Webb will ultimately reveal. The data it is collecting on Jupiter right now, in 2025 and 2026, is being analyzed by teams across the world, cross-referenced with Juno spacecraft data, compared against Hubble observations, and fed into new computational models that are trying to make sense of a planet that keeps defying its own predictions. According to informed sources within the planetary science community, the coming years of Webb observations of Jupiter are expected to focus specifically on the deeper atmospheric layers, the transition zones between the upper stratosphere, where the new jet stream was found, and the lower cloud decks that are visible in optical images. These transition zones are where the energy exchanges happen, where the jet stream interacts with the cloud systems below it, where the auroral energy deposited at the poles redistributes itself through the planet's circulation. And right now, that region is essentially unmapped territory. We are looking at it for the first time. The real story, the one that the headline about a strange discovery only scratches the surface of, is that Jupiter has been hiding entire dimensions of its complexity from us, not because of any concealment, but simply because we lacked the instruments to see them. And now that we have those instruments, the discoveries are arriving faster than the models can accommodate them. Every answer Webb produces comes with 3 new questions. Every feature it reveals suggests another feature we have not yet looked for. The Great Red Spot is dying, and we do not know what takes its place. A jet stream 3 times faster than a Category 5 hurricane is roaring above the cloud layer at an altitude we never studied before. An aurora blazes with an infrared light so bright it dominates Webb's instruments, and simultaneously leaves no trace in Hubble's ultraviolet. Cameras, an impossibility that has no current explanation. The ocean of Europa, once the most hopeful location for extraterrestrial life in our solar system, may or may not have the geologic activity it needs to support biology. And the spacecraft that will give us the definitive answer is still 4 years away from arriving. Every data point is a question. Every image is an argument. Every discovery is a doorway into a deeper uncertainty. And perhaps the most unsettling thought of all, the one that responsible scientists are reluctant to say out loud, but that the data increasingly suggests, is this. If we are still finding fundamental, previously unknown features of a planet we have been studying for 4 centuries, in our own solar system, right next door by cosmic standards, then our confidence about the billions of other planetary systems scattered across the galaxy should probably be considerably more humble than it currently is. Jupiter is not behaving the way we thought it would. Its atmosphere is hiding structures we never predicted. Its auroras are producing signals with no known explanation. Its moons are challenging everything we thought we understood about the conditions for life. And somewhere above all of that, 320 miles per hour, a river of wind 3,000 miles wide is howling through Jupiter's stratosphere. Silent, invisible to every human instrument that ever flew past it, present perhaps for millions of years, and we only just found it. What else is already there, waiting for a telescope powerful enough to look?